Hello and welcome to this video abstract. I'm Dr. Robert Boschra, and I'm the lead author on the open access article published in Brain Communications titled On the Time Course of Functional Connectivity, Theory of a Dynamic Progression of Concussion Effects. The paper discusses work conducted at the Language, Memory and Brain Lab and the Ariel Research Center in McMaster University, Ontario, Canada. A surge in interest in concussion has developed due to the recent association of the injury with severe consequences on the brain long after injury. This refuted earlier views of concussion having a purely transient effect on the brain. Despite the prevalence of the reported effects of concussion, specific characteristics of the injury and neurophysiology were often inconsistent. That was amplified when considering results from different experimental designs, age groups, and assessment modalities. Our study aimed to inspect one primary variable, the time since injury. The hypothesis was that the effect of concussion on the brain immediately after the injury would be different in comparison to the effect decades after. To examine this hypothesis, we used two datasets, with 93 subjects in total. The acute dataset contained 26 adolescent participants who were concussed an average of 20 days prior to testing. For this cohort, we collected data from 20 healthy controls for comparison. The other dataset characterized the long-lasting effects of concussion by examining 19 retired professional football athletes, 20 years separated from their most recent injury. Data from 20 matched controls were collected in this dataset. We examined the effect of concussion on neurophysiology using electroencephalography, EEG, during an active oddball task. We used coherence and weighted phase lag index to inspect the functional connectivity in the delta, theta, alpha, and beta bands between different electrode clusters. Results confirmed the hypothesis that the effect of concussion on the brain changes over time. This was pronounced in the connectivities calculated by weighted phase lag index in the delta, theta, and alpha bands. Interestingly, there was a prominent interaction between the concussion variable, concussed versus not concussed, and the age group or cohort variable, acute versus chronic. We found a characteristic hyperconnected brain in the acute stage compared to matched controls. On the other hand, concussed participants in the chronic state conveyed lower functional connectivities compared to controls. This confirmed and augmented earlier reports that concussion has a non-static effect on the brain, which, upon examination, may indicate when and how a brain adapts to injury. In order to understand this pattern of changing functional connectivity in relation to prior evidence, we developed a theoretical model of the decline of cognitive capacity following injury, its apparent recovery by compensatory mechanisms in what is described as the post-acute stage, and finally deterioration as cognitive reserve is unable to sustain the mentioned compensation mechanisms. We also related that to our findings in the scope of other studies of functional connectivities using modalities such as fMRI, and finally related the model to results from the literature in resting state, EEG, event-related potentials, behavior, and others. This theoretical model synthesizes the various lines of evidence that at first appear to be in conflict and offers a starting point to target specific research questions that account for the dynamic nature of the brain in its recovery from concussion. If you'd like to know more, you can find the full open access article on the Brain Communications website. And if you have any further questions or comments, do not hesitate to contact one of the two corresponding authors, myself and Dr. John Connolly. Thank you.